So the major differences when we do those calculations, after we know what our mu is based upon the sample means, is that I'm going to have to remember that I'm no longer just using sigma. If it is that I'm taking for a sample, I have to use sigma divided by the square root of n. So again, here we go. It's just giving you that normal distribution, an example where it's already normally distributed. It doesn't matter what my sample size of 10, I'm still going to have normal distribution. Sample size of 50, obviously a closer, neater normal distribution. If I started with a uniform distribution for my population, as I get to n, oh, it's getting there to be, but look at when by the time I get to 50. It does have a normal distribution. So it wasn't even normal to begin with. Then I could even have a U-shaped. Even with a U-shaped distribution of a population, n of 10, I'm already approaching that normal distribution, and an n of 50, I'm there. So that's the neat thing, and that's why the central limit theorem is used so much. Okay? So here we go. Let's do an example here. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. How many times have you got into an elevator and it states that? Maximum so many people, maximum weight, right? Well, how do you know that those 16 people aren't going to weigh more than 2,500 pounds? Right? Okay. So assuming the worst case scenario in which the passengers are all male, what are the chances that the elevator is overloaded? High. Oh, did you just divide it? Did you just pick up your calculator and... Ah. Yeah. Wow. You're not big. You're not big.
But so I can imagine a male most likely will be at least 180, 200.
Ah. So see what you picked up on already is that, yeah, that's a concern. If I got into an elevator and it said 16 passengers, but the total weight is 2,500 pounds, just do a real quick calculation. If they're all males, just say 200. What's 200 times 16? 3,200. Oops. Right? Ooh. Okay, so now see how that works? Now, but maybe they're not going to be all men.
If I'm on an elevator, I'm looking at it and looking there, I'm going to be, you never know, so you want to make sure that you look at that in that perspective.
You want to set the worst case scenario for safety. Ah, okay, so assume a male weighs as follows with a normal distribution of a mean weight, 182.9, and a standard deviation of 40.8. That's a pretty big range. Think about that normal curve. Okay, one standard deviation away is another 40 pounds. Wow. Okay. So find the probability that one randomly selected male has a weight greater than 156.25. Why 156.25? Because if you put in your calculator, that's 2,500 divided by 16. That's, according to this, they're assuming that's the average weight, right? Okay, so what is the probability that one randomly selected male from the population will have a weight greater than 156.25? This you've already done. We've done it and done it. And you guys can do it very quickly, I'm sure. Here's my normal curve. We always start with that, right? What's mu for the males? 182.9 with a standard deviation of 40.8. Okay? So if I wanted one standard deviation this way, I would end up with 222, 223.7. And just one standard deviation this way would be 140, nope, 139, nope, 140.1. Okay, so I just haven't, I'd like to put those values so I just know where I am on my curve. It just helps me to draw that picture and think about that. I want to know the probability of randomly choosing one that was 156.25 or greater. 156.25 is going to be somewhere in here. Do you agree? I can't remember the number. 160, okay, I was right. 156.25. And I want it to be that much or greater. So I'm shading the right. What am I looking for? The probability, which is really the area. So I'm going to my distribution, going for my normal curve, and my lower end is going to be 1.25, perfect. My upper end is going to be, and my mu is 182.9 and 40.8. 0.7432. As Jemai said, that's really high. So just selecting one individual for the entire population of males, I have almost a 75% chance that they're going to weigh more than the 156.25. I don't know if I want to get on that elevator.
First question is, we have any, like, this kind of reminds me of like the usual and unusual in a way. Should we still use that 0.5 or the 0.05 to kind of like, or just use common sense?
Well, in the problem like this, you're going to use common sense.
And another question is,
So put yourself, would you want to get on that elevator? Okay, there's your answer.
and another question is, this is just like what we've been doing. I thought it was
Absolutely.
different.
It is, because part B is going to be different.
Okay.
Ah, okay. So that is nothing new. That's what we've been doing. That's what we've worked on all through 6. Right? Perfect. But part B says something different. Part B says find the probability of 16 males have a mean weight greater than 56.25. So all of a sudden now, I'm not choosing one male out of my population. I'm choosing a sample. The sample is 16. I'm choosing 16 males. And I want to know what's the probability that that sample will have a mean weight greater than 156.25. Well, let's do some keywords here. because you need to know the difference in when I'm going to use the central limit theorem and when I'm just going to use what we've been using all along, normal curve. Okay? Normal curve, I have one randomly selected person. That's what we've been doing. Now I know I have to use the central limit theorem simply because it says I'm taking a sample. I'm not choosing one individual from the population. I'm choosing 16. I'm choosing 16. Soon as I know that I'm choosing 16, I have to do another calculation. So in part B, that was the key word, sample of 16. As soon as I see that, I know I have to change my sigma. I have to change my standard deviation. Okay?
So that first one was for only one person.
The first one's for one person. That's what we've been doing. Now I'm taking a sample. So I have to change sigma. I have to change my standard deviation. Remember what it is? It is sigma divided by the square root of n. Okay? So in this situation, sigma was 40.8, but I've got to divide it by the square root of n. And how many people in my sample? 16. Somebody run that through your calculator. Wow. So just to reiterate here what's happening, if I use the same units of measure and I was up here and I had a sigma of 40, I'm going to have this stretched out curve because my standard deviation is so large. When I change it because I'm taking a sample, central limit theorem, my standard deviation is now a lot smaller. So if I use the same scale, I'm going to have something more like this. Whoops, I should still make it symmetrical. So I've taken this and squished it in. The reason I'm allowed to do that is because of the central limit theorem, because I'm taking samples and not one individual. Okay? So now I'm going to say 186.2. What's the mean? What's the mean? 182.9. See, I can't remember these numbers. But now my standard deviation is not 40.8. My standard deviation now is 10.2. Okay? So one standard deviation up is going to end up to be 193.1. One standard deviation down is going to end up being 172.7. Okay? So I've squished them in, haven't I? Well, okay, do two standard deviations down. I'm going to subtract another 10.2. I'm at 152.5. Yes? 162? No, it's, oh, yep, you're right. I was subtracting 20. 162.5. Well, guess what? What is my average weight up here? I want to know if it's 156.25 or greater. 156.25 or greater? I think I'm in trouble. I'm already down 2 standard deviations, and I haven't reached it yet. Because 156.25, Wow. See how much that's going to change that? And I want 156.25 or larger. All of these people, these samples, all of these samples of 16 men would have an average. Wow, that's scary. So let's find out how many. Let's find out how many. Go into your calculator. My lower end is still 156.25. My upper end is still 9999999. But the mu stays the same, but the standard deviation now is 10 point. It is. I have to remember that I can't use the back key on my keyboard. Sorry about that. So second distribution. $156.25. My upper 9999999 with mu being 182.9 and the standard deviation being 10.2. My area under the curve is 0.9955. Which means that if I take a sample of 16 men, 99.5% of those samples are going to exceed the weight limit. I'm not getting on the elevator with 15 men when they're assuming the average is 156 pounds. Right? All right.
Just to clarify, you don't have to do like an example of A or to get B.
No, they're independent. You don't need to do one to get the other, but you need to know the standard deviation of the population and the population mean.
So the sample mean and the population mean are going to stay the same?
Yes. Sample mean and the mean of the samples is going to then is my good predictor of the mean of the population, and that's why. Okay? That makes sense? Did I finish the problem? I can't see it anymore. Oh, good. Okay. All right. Is it making sense? It's not too bad, is it? So, loading M&M packages. M&M plain candies have a mean weight of 8.8565 grams and a standard deviation of 0.0518 grams. The M&M candies used in the data set, we don't even need the data set because it gave us everything, came from a package containing 465 candies. The package label stated that the net weight is 396.9 grams. If every package has 465 candies, the mean weight of the candies must exceed 0.8535 grams for the content net weight to be at least 396.9 grams. Okay? If one M&M candy is randomly selected, find the probability that it weighs more than 0.8535 grams. Go ahead and do that.